All right, now we've covered all the things we're not supposed to talk about. Let's go and proceed to our next sorting algorithm. Now I been jumping around a bit, mainly for your projects, to make sure you have everything you need. By the way, how is Project 1 coming?
Not bad.
Not bad.
Better than last time.
Just needs a little bit of help.
With a little bit.
Just a little bit.
Just a little help.
Sure.
You just need to implement 2 functions and you'll be good to go?
Just function and a half. Function and a half.
Function and a half? Oh, okay.
I mean,
All right.
at this point, it seems like my stuff works. I'm just doing test cases to be sure.
Great.
I need to put down one.
Okay.
Mine's done, so I'm just
Moving on in life?
Yeah, same.
Okay.
I don't know if it's done, but.
All right. Well, I'll sign Project 2 on the Wednesday. That way you don't have to. All right, fine. You want me to sign it today?
No.
No.
You sure? I can sign it now. I mean, I don't mind.
When is it due is the question.
Probably 3 weeks.
You just want me to cry.
Right.
You're
I
really
told you.
pushing for
I've
it.
showed you what my favorite beverage is, right?
Yeah.
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 Come on.
I'll bring those into you one day.
Thank you. All right. So last time we talked about bubble sort, which was probably kind of a, well, it was nice in that it was simple, but there are definitely other sorting routines. So go ahead and give me a list of some numbers.
12.
Not sorted, of
5.
course.
14. 2. 0.
How many is that?
6.
Let's keep going. At least 8. 2 more.
Negative 20.
Negative 5.
Okay. So if you were to sort these, not write a program, but someone gave you your cards and they all had these numbers on them and you wanted to sort it, how would you go about doing it?
Drag and drop.
Drag and drop which one?
All of them.
All right, so you find the lowest one first, which is
Negative
negative 20.
20.
And then you, which one's next?
Negative
Negative
5.
Negative 5.
0. 2. 5. 12. 2.
Okay.
Hey, you forgot 20. Yeah.
Yeah. You missed one though, dude.
Human error.
That's why we have a computer do this,
This
right?
isn't human.
Wow. Thank you. I mean, yes.
He
All
lost
right.
his soul a long time ago with all those children's tears.
Good. Or does it feed my soul and keep it? No, it does not.
No.
All right. So this method of sorting, which is intuitive to us, is going to be the next sorting algorithm we will talk about. It is called, there we go, selection sort. Rearrange the list by selecting an element and moving it to its proper location. So you got to find the smallest or largest and move it to the beginning. Can also be applied to linked lists. Hey, look at that.
Cute.
Oh wait, all right. What's that?
I tried that this weekend. I struggled.
You struggled to do selection sort?
On a linked list, yeah.
Oh, okay.
With names.
Hmm.
Yeah.
Mm.
Yeah.
You do know vector has a sort routine, right?
What? I could use that?
Yes.
It's fine.
I mean, I sorted as I was adding.
Who needs
that-
to sort?
What?
Who needs to sort?
Who needs to
Yeah,
sort?
I mean,
Why
let
would
them
that be
decide
helpful in
something.
Project 1? Anyways. All right, so let's go back because this discussion is going to be interesting and short. What's the big O? How long did it take us to find the first one? To find it. In. So I'm going to make, where are we? Comparisons? So it took O of n to find this one, number of comparisons, because we had to compare the whole list. How about to find negative 5?
N minus 1.
N minus 1.
N minus 2. So on.
So what's the big O of that?
That's a lot of N's. Yeah,
That's a lot of n's, so. Wow, that was a terrible.
N. No, it'd be 0.
Right? Anyone remember this formula?
It's been a while.
Hmm.
Plus 1.
This formula is just going to keep coming back. What's the big O of that? Am I off the screen?
Oh,
Yeah.
N squared plus N over 2.
No, that's squared.
What's the big O? N squared. Sure. All right, fine. And since it's big O, we don't care about that. We don't care about that. All right. So that means for comparisons, it's O of N squared. Hey, that's the new O with a little hat. All right, how about swaps? So that's the number of comparisons we had to do with N squared. Am I still on the board? Sweet. How many swaps do we have to do? So we compared it all, and then we swapped -20 with -5, right? And then we did a bunch of comparisons, and then how many things did we swap? Just, well, hold on. I think, let's start from the beginning. Going a little fast. So we compare all the numbers on the first round, right? And we find out which one goes to the beginning. We find out that it's -20, right? And then we swap it. So that's one swap. And then we compare everything that's left, find the smallest, and then swap that. Combine everything and swap that. So the question is, how many times did we swap? 7 times. But if you have a list of size n, how many times would you swap?
N minus 1.
Which is big O of n. Right.
These constants don't matter.
Right. So, does anyone remember what the number, the big O for bubble sort was?
N squared.
For comparisons and how many swaps? How many times could you swap while it was bubbling up? Because you could do it in times, because since it was bubbling from the beginning, like it bubble, 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 all the way up, each time you could be doing n swaps, which means that for bubble sort, the swapping was n squared. So this algorithm is already better. All right, let's see what the slide tells us to do next. Oh, good, we do a little big O analysis for swapping. No, not for swapping. Yeah, for swapping. And you do it n minus 1 times because you only swap once per iteration. And finding the minimum location, you got to go through everything. And that's why it's, hey, there's the formula again. Oh, they do n minus 1. That's right. Because it's not, it doesn't start at n, it starts at n minus 1. Sure. But it's still a big O of n squared. Oh, good, we get to watch it. So insertion sort for an array. Wait a minute. Okay, those are not sorted. Great. All right, let's go to the board. We're going to do this for an array. And I'm going to show you each iteration. That way when you're on your midterm and you have selected selection sort, and I've given you 10 numbers, you'll know how to sort them and get all the points for that question, okay? We're about ready to do this question on the board. Everyone got it? Okay, good.
All the points.
Yes. So we need to move the -20. And what was the -20 swapped with?
-5.
-5. So we put the -5 here, 12, 5, 14, 2, 52, 0. Great. Now we need to find out what goes next. What's the lowest one? Hey, -5. All right, so we write the line again. And just for emphasis on the board, though I'm not going to require you to do this, that's in the right place. We move that to the right place. What's the next one? What goes here?
0.
0. So where's the 12 go?
Back.
Where the 0 was. All right. All right. What's next?
The 2.
And where does the 5 go?
Where the 2 is.
Where the 2 was. same page. What goes next?
12.
And that swaps with 14. And then what's next?
14.
All right, the 14.
I'm about to fall off the bottom.
Well, we're done.
Oh, well,
Because
good.
an array of size 1 is already sorted, right? That's a nice property.
So you never actually
I
check
sure
the
hope
last
so.
one, right?
You don't have to. You don't need that one last iteration because if your array is just 1, there's something to yeah. You don't. An array of size 1 is already sorted. Okay. Any questions? Nothing? All right. I'm going to erase this. Okay.
Let's go.
And it's gone. All right, so hey, look, we're at this point. I'm trying to figure out what they're trying to do. That's insertion sort. I knew I was confused. Let's do insertion sort next. So insertion sort, it's best to think of it as you're building the array up. So, first off, we're going to start with the beginning of the array, -5. And I'm going to start higher because that way I may run out of space. Oh, I got a better idea. Watch this.
Idea of the century.
Whoa!
There you go.
All right. I'm going to move this trash can out of the way before I fall down.
Let's try to sabotage me.
All right, so we'll start with -5. Hey, look, that's sorted. Great. Let's add -20. Where's -20 going to go in this list of -5?
Before -5.
Before the -5. So it goes -20, -5. How are we doing?
Great.
Then comes the 12. Where's the 12 go?
After -5.
All right. Great. Now let's add the 5.
It goes in between the last
5,
Yeah, right there. How about the 14?
the end.
Now the 2?
In between -5 and 5.
All right, I'm going to pause here for a moment because I've been doing a list of numbers. What are the 2 ways that we can store this list? Linked list and array. If we need to put the 2 right here, which data structure would be better for that? A linked list. Why would an array be a poor idea? Or poor?
Because you have to shift all the elements down.
Shift all the elements down. Well, a linked list, you just put it right there.
Yeah.
There's your big hint for the day.
Big hit. Never use
Big.
arrays, ever.
Great. And what was next? The 52? Where's that go?
The very end.
Very end. And then 0.
After -5.
Right. Again, which data structure would be better for this?
Linked list.
Okay. What? 2, sorry. Okay. Somehow it just became the same size right here. Whatever.
It's fine.
Yeah, whatever. Yeah, it's fine. All right, so now we need to do our big O analysis of this. So this was selection sort over here. Let's do, am I too tall? No, good.
You forgot a 14 somewhere along the way.
Huh?
You forgot a 14 somewhere along the way.
Ah.
Every time.
No,
You said-
it died. Yeah, the 14 died right there. Yeah, look at that.
Oh, I forgot important. That's why it became the same
It is the least
size.
important number.
Whew. I don't remember that being a good age. 14.
Yeah.
That was a little rough. 14?
Eight.
8th grade?
I think so.
Oh yeah, so do schools go middle school from 6 to 8 here? Or do they have 9? 6 to 8. So then 8th grade, you think you're the king of the world, yet you're 14. So you're, I'm trying not to say a terrible person.
I realized
but,
that I wasn't.
but yeah, that didn't work out well. All right, so insertion sort, which is what this is called, because every time you're inserting the new number into your list, hence insertion sort. Let's go down here. How many possible comparisons could there be in order to add a 0? What's the worst case, is my question. Right, in. It could have gone to the end. What would be the best case? 1, right, because you compare to the first and say, oh, it just goes in front of that. And then you'd be done with comparisons. So n minus 2, n minus 2 minus 1, n over 2. Whew. N divided by 2, n divided by 2 over 1, et cetera, et cetera, et cetera. So that's going to look very similar to the summation over here, except for it's divided by 2, but that's inside of let's go ahead and write this out. I equals 0 up to n of I over 2. Roughly, average case is what I'm saying. Which, if you decide to do that again, it's, what is it? I over 2. Oh, we have to divide everything up. Do that. Do you want to do that?
No.
No, no one wants to do that. I think something like n over 2. You're still going to multiply those n's and eventually get an n squared, right? So the big O of this is still n squared. I answered that question for you, for comparisons. Does everyone see that? All right, how about for swapping? Oh,
Real quick, this is insertion sort?
insertion, yes.
And what was the first sort that we did?
Selection, because you're selecting where it goes. Selection sort is the intuitive sort, is what I call it, because as a human, that's the default sorting you go to. Let's just find the lowest one, put in the right spot, the next lowest one, put in the right spot. Which, by the way, is not necessarily the fastest. I've always wanted to get a bunch of cards and run quick sort and see if that actually goes faster. But anyways, back to here. So it's swapping. How many swaps were there? Well, you had to insort it. So you had to take it out of this list and put it into this list, and that's what we're calling as a swap.
But then don't you have to also compare whenever you're putting the next one in to see which side it goes on?
So that's the compare part.
Oh, okay.
So we've already said the compare is n squared, just like with selection sort. So now we're talking about, the number of times we swap, like from here down to here, or any other swapping we have to do in here.
Is it just n then? Or n minus 1?
So that's a half truth. Think about this a little more carefully. How about I'll ask you this question. It's O of n for which data structure?
Array? No.
Well, if it's not array.
For linked list.
Linked list, because you swap from here down to here, and you don't have to update everything else. Remember when the 0 got here, what do we have to do with all this? If it was an array, shift it down, which means you may have to swap n times. So, for a linked list, it's O of n. For an array, it's actually going to be O of n squared. Hopefully that tells you which sorting algorithm not to do on an array. But does that make sense why the array would be n squared? Because when you insert, you may have to shift everything down, which is more swapping. All right. Good. And this is why I find this lecture hilarious, because that's it. But we'll go through another example. So insertion algorithm. So the way you actually do insertion, and on the board is probably a good way to think of how you do a linked list, the linked list version, because I was building the array from the list from the list up there. But with an array version, you're actually going to build it in place. So for example, they have 10, 18, 25, and 30. Let's just say we've sorted this. Then you want to add the 23. So we know that we need to move the 23 to the 25. So what actually happens is you take the 23, make a temporary copy of it. Then you copy the 30 over and then the 25 over. Warning, when you do this for your lab, you want to copy from the 30 side over, not the other way. Because if you start with the 25, then you're just copying the 25 to the 30 and then the 25 again to the 23 because you just overwrote the 30. So make sure that you start at the 30, copy the 30 over, then copy the 25 over, and you have to keep going, copy the previous number over. Otherwise, no worky. All right. And then, now that everything's been copied over, hey look, there's two 25s. You can copy the 23 in, and now it is sorted. How are we doing? Hopefully you can see if the list was 1,000,000 elements long and you had to copy 250,000 for every iteration, things are going to get slow.
And this is obviously different and easier if you used a linked list where you just plugged it into the...
Right, you just update the pointers, right? Yeah. Yes.
So for the lab, are we gonna have to use an array and do it this way, or are we gonna be able to use a list?
Your lab is you need to write selection and insertion sort for your array list. Then you need to write a sort function which chooses bubble sort, selection sort, and insertion sort and calls one of them based on which one you think is the best. Then you need to update your linked list class and implement one sorting algorithm for it.
Huh.
Hopefully I've given you plenty of hints of which one that is. Or I'm sorry, which one I recommend. You can do insertion for, wait, I shouldn't say things like that. You can do it. You can do any of them. Actually, any of them
You
would.
can do anything, but
You're an engineer. We can do anything. Have you all seen that video? They got the engineer down. They're like, all right, we need you to draw, what was it, 12 lines, all perpendicular to each other.
oh,
What?
Half and he goes, that can't be done. No. You're the engineer.
do it.
You can do this. It's like, no, that can't be done. No, let's not get crazy now, all right? We got money. We're giving you plenty of time. You can figure this out. And then at the end of it, he's like, sure, whatever. And the lady goes, can you make one of the lines in the shape of a kitty? Everyone loves kitties. You've worked, right? Have you been in this meeting before? No, this meeting will happen one day.
No, they just give us like a vague of what they want, and then they're just like, go.
Oh no, that's normal. So that's
Yeah.
good. That's good. The bad ones are what I just tell you, where there's going to be the meeting where they're going to ask you to do something that's impossible, but they don't understand why it's impossible. And if you try to explain to them why it's impossible, they won't believe you.
Because physics.
Yeah, exactly. Right. 12 perpendicular to each other. Wait a minute, what? I don't think you understand what perpendicular means. All right. So analysis of insertion sort. Best case key comparisons n minus 1. That's if you every time you compare it to the first one, it just went in front of it, aka the list was in opposite sorted order. But worst case would be the good old summation formula we had. So the average case happens to be about half that. So it's still n squared. And we did that at least with a little hand waving up on the board. When you take algorithms, we'll go more into that. All right. So this is, let's see, your sorting algorithms for the array, not for the linked list. Hey, so just looking at the board, which one looks like the best for an array?
Selection.
And why is that?
It's bubble sort.
Because it's the only one with n number swaps instead of n squared.
Right. So someone said bubble sort, and they're being slightly facetious, but actually not complete. But that's not completely true. What is one advantage of bubble sort?
It's simple.
It's simple. So if you had to code something straight from memory, and it had to work the first time, otherwise everyone dies, or something, you know? Right. Bubble sort.
That'd be a boring movie.
You have
That would be he's
hour before
just
the
sweating,
program
going
begins.
down as he types each key. They try and make everything.
You
dra-
see him on a computer typing lines of code, little sweat.
No, you gotta make it.
Yeah,
You gotta make it dramatic. So every time he hits the key, like something happens in the real world, or explosions go off, dramatic
Yeah.
music. Yeah, I mean, whatever. I'm like, all right, we need. All right, we're gonna have a new. Was it student come and look at the computer science department? We want you to show them the labs. I'm like, you do realize they're just a bunch of computers lying around. I mean, what do you want me to show them?
That we have one.
I mean,
That they exist.
it's not exactly a spectator sport. If you, yeah. Ooh, the comparison tree. We're not going to do this.
Fantastic.
And then we'll do quicksort. Great. Let's stop.
Is it actually quick?
It's faster than the other ones.
All the time?
We'll get to